All right, as promised, let's talk about our different forms of energy and the different equations that we're going to see as we move through the semester. So we're going to see two forms of each of the equations for kinetic energy and for potential energy. So the first form of kinetic energy is an object moving relative to the surface of the Earth, and that is going to be E sub k equals 1/2 mv squared. So maybe you've seen this before in physics. We use an E sub k to represent kinetic rather than saying ke, just to keep our notation consistent. So E sub k itself is going to be the kinetic energy, and that is in terms of units of joules. M is going to be the mass in terms of kilograms, and v is going to be the velocity in terms of meters per second. So you'll notice we're completely in SI units as we do this example. We would have different energy units if we were doing this in terms of feet per second or pounds or something like that. The second form of kinetic energy that I want to talk about is something like a fluid moving with an m dot. So this will hopefully be new because this makes it fun to teach and interesting to teach to you, right? When we have an m dot, we also end up with an e dot, an energy flow in the system, not just a static energy measurement. So we're going to see the exact same equation, but our variables have changed slightly. So E sub k is now the kinetic energy flow rate. So that's joules per second. The mass flow rate is in terms of kilograms per second. So we put the m dot in there instead of the m, and then the velocity stays the same. So you'll notice there's no v dot, right? There's nothing going on with the velocity because that's already in terms of meters per second. Where we add the dot is on the mass flow, and that turns it into an energy flow. So that's important to know going forward. So take a pause to make sure that you've labeled these equations in your notes so that they are nice and clear going forward, because we're going to use these a lot. Next, let's talk potential energy, and we are specifically talking gravitational potential energy in this class. Remember that there are other forms, but they don't necessarily matter to us with the types of system we design. So we're going to have two forms here as well. We're going to have an object with mass m that has a potential energy, and that potential energy is going to equal mgz in this particular system. So E sub p is going to be our potential energy in joules, m is going to be our mass in kilograms, z is important, or z if you prefer, is going to be the height above a reference point, and that is in terms of meters. So this is going to become really, really important when we solve problems. That reference point is going to be really, really critical because we're not always measuring potential energy with relative to the surface of the Earth. Sometimes it's something different. So we need to be careful about that. And then G is the gravitational constant, and that's meters per second squared, and that's 9.81 when we are talking about SI units. The second form of gravitational potential energy is an object or a fluid moving with a mass flow rate. So same as kinetic energy, we've now changed this to a flow of potential energy, and mass is the only thing that can have a flow rate. We can't have a flow rate of height. We can't have a flow rate of a gravitational constant. So that's why you see that dot over the m, because it now has to be a mass flow rate. So we're going to see a potential energy flow rate, and that's in terms of joules per second. We're going to see the same gravitational constant and the same height above a reference point, but now we also have a mass flow rate. So that's important here. So take a second to make sure that you've got all of these equations in your notes and you know exactly what all these variables mean, because we are going to use them consistently throughout the semester.